Welcome back to the series. This is lesson 3 in our Net 1010 digital logic module. In the last video, we looked at how transistors work and how we can use transistors to construct logic gates. But at the very end, we found that for the most part, we actually don't use logic gates in that way. We have ICs or integrated circuits that have that transistor circuitry built into it, which allows us to really quickly make use of logic gates. And we'll see down the road how we have ICs that give us a variety of different functions, not just logic gates. But to start off, we're going to do a few exercises with specifically the NAND gates and the 7400 IC, which contains 4 NAND gates inside of it. So at the end of the last video, we had just looked at the 7400 and saw that yes, indeed, it does have some NAND gates in it. So now let's discover some fun things that we can actually do with those NAND gates. Now, if you look in your workbook, I've got this open here. I have just released an updated version of this workbook because the exercise that I'm about to show you in the old version didn't work with this specific NAND gate IC. So if you have the old version prior to May 14th, 2020, make sure you go into the D2L and grab the newest version. It should be updated there in content. What we're doing here is creating an oscillator using just NAND gates and a few other bits of hardware. What an oscillator does, what it means to oscillate, is just to move back and forth. That's what the term means in general. In electronics, typically when we talk about oscillation, we're talking about voltage going from low to high and low to high repeatedly, on and off. There's a variety of applications for having an oscillation. Very simply, you can have a flashy light, a blinking light for whatever use you have for that. But if you think about more complex systems like a computer, where a lot of functions need to be in sync with each other and kind of timed together, we use oscillators to generate a clock signal, it's called, which just keeps everything moving at the same time, tells everything when to move on to the next step. So a very useful thing to be able to have, and we'll see how we can make that out of just NAND gates here. So the circuit diagram that I have in your workbook, this is the updated version, and let me just zoom in here. So this is the circuit we're going to build on our breadboards. You'll notice there are 3 NAND gates here, and that's fine because our IC, the 7400, has 4 NAND gates built into it. So we're only going to need one of those. And in addition to these 3 NAND gates, we have 2 resistors and a capacitor. And you'll notice down below, I've written what resistors to use and which capacitor to use. And you can later on try switching these out and seeing if that changes anything. Well, let's hop over into Tinkercad circuits and start building this. So you'll notice I just have the 7400 in my breadboard here, and it's connected to my Arduino 5 volts and ground. One thing you might need to do with your ICs before they can actually go in your breadboard, you might need to bend some of those pins inwards a little bit. Easiest way to do that is just hold it very carefully, place it sideways on your desk, and just give a little bit of pressure, folding those legs inward just a little bit. Do that on either side until they go nicely into the holes on your breadboard, just like this. The first thing we need to do with this IC is hook it up to power and ground. That's the only way the NAND gates inside will actually work. And we will remember from our pinout diagram that pin 14 here is VCC, which is for power, and pin 7 is ground. So on the breadboard, that looks like this. This one is pin 14. Remember, we look for the notch and we start to the left of that. If the notch was facing up, we start to the left of that. This is pin 1, and we count down this way and up this way. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So pin 14 is power, so we will connect that up here. And I'll just do some nice color coding. Keep this maybe a little bit out of the way. And pin 7 here to ground. That's that, simple as that. So let's start looking at our circuit diagram and start connecting some of these things up. Now, the first thing I notice when I'm looking at this is that the inputs for all 3 of my NAND gates are connected together. So that's an easy thing to do right away on the breadboard. Let's tackle that. We'll take a look at our pinout here. Well, remember we have 4 NAND gates to choose from, and it really doesn't matter which ones you use. It just kind of depends on exactly how the layout's going to work. So the ones that I'm going to use are this top left one and the 2 on the bottom here. So I'm going to go ahead and connect together the inputs of NAND gate number 1, the inputs of NAND gate number 2, and the inputs of NAND gate number 4 to make these connections here. There, there, and there. So very simply, this is the input of that top left one. The bottom left one, inputs connected together, and the bottom right one, inputs connected together. So now I've done a bunch of these connections. Let's see what else we're doing. The output of the first gate is going to go into the inputs of the second gate. Well, I'll just decide that this bottom left one is going to be my first gate in that chain. And I'll take the output, which is this one, and just connect it to one of the inputs of the second gate. Let me color that purple. I'll do the outputs of these logic gates in purple and connecting the inputs in this green. So this little purple wire that I've put here is this connection right here, connecting A to the inputs of B. And it doesn't matter which of these inputs I connect it to because they're both connected anyways. So I could do this instead. Doesn't really matter at the end of the day. I could also connect here to here, here to here, and not have this one if I really wanted to. Same number of wires, doesn't really matter. I think that this way it looks a little bit cleaner, is a little bit more clear what's going on. Let's move on in the circuit diagram. We'll see in the same way that the output of B is connected to the input of C. And there's something else going on here as well, but let's just handle this connection straight across. So the output of this one is pin 6 here, and I will connect that over to the input of this one, and I'll once again do that in purple, just to keep things obvious what I'm doing. So now we've got all of these connections on the top going on. All that's left is to hook up these two resistors and the capacitor. And it might look like these are all going to ground because they're going to like the bottom of the circuit diagram. But notice there's no connection going to the ground symbol or anything that says G and D. So they're actually not going to ground. They're just all getting connected together. And so we'll do that in a row on the breadboard somewhere. So let's start with this very first resistor, R2. It's supposed to be a 10K ohm resistor. Ignore this note here. We're just going to have them both be 10,000 ohms. So the way I'll do that, I'll grab a resistor. I'll make it a 10,000 ohm resistor. It's going to look a little different than yours because yours are the 4-band color codes. So just grab one of the 10Ks. It's the one with only one red stripe on it. And I'm going to connect that from, let's take a look. This is coming from the input of the first NAND gate. And then it's going to this, whatever this common connection place is for all three of these things. So I've already planned this out beforehand, so I know where I'd like to put this is right here and into this row. And I'll just make this gray so it looks like the leg of that resistor. So it's going from one of these inputs on our first NAND gate and up to just this random row on the breadboard. Anywhere will do as long as it's not connected to anything else. This is just going to be where we're going to connect all three of these components, this resistor, and this capacitor. Okay, well, let's do the other resistor here. It's also going to be a 10K ohm resistor, and it's coming from the output of the last NAND gate. So I'll go ahead and grab another resistor. I'll make it 10,000 ohms. Again, yours will look a little different. And the output of my last NAND gate is right here, which is pin 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. If we look at our pin diagram, yeah, pin 11. So I'm going to connect it to pin 11 and put the other leg over in this random breadboard row that I'm using to connect things together. And one thing I'm seeing right now is actually that's hiding this purple thing, so I'll just move it up here. There we go. And now the last piece that we have is this capacitor. This diagram shows a non-polar capacitor, and I think actually I even said non-polar in here, but in order for this to blink at a rate that we can actually see with our human eyes, we need to use a 10 microfarad capacitor, which you don't have in non-polar, you have in just the polar kind. And remember that capacitors are the ones that look like this. You're looking for the one in your kit that has a stripe down the side, and you should see somewhere on it 10 UF, just like this, with a lowercase u. Okay, there are other black cylinders in your kits that do other things. They're not capacitors, so just be careful that you're grabbing the right one. And what we're going to do here is we're going to take the positive leg, which is the one that is not where the stripe is, and it is probably the longer one. And we're going to connect that into where? We're going to connect that here into either the output of the second NAND gate or the input of the third NAND gate. It really doesn't matter because they're both connected together anyways. So I'll put it just into here where the input of our third NAND gate is. And the negative of this is just going to go here to this random row in the breadboard where everything else is connected. Okay, so now I have this all set up. It looks like exactly what this looks like. So theoretically, this should work. What should happen is if we turn this on, wherever this is, which is the output of our third NAND gate, should be giving us an oscillation. Just like this picture, it's going to turn on and then off and then on and then off and then on and then off again. But right now, we don't have any way to actually see that happening. So what we'll do is just for visualizing it, we'll just quickly hook up an LED and a current limiting resistor. So this is, again, that output. I'm just bringing it over here just to keep things a little cleaner. I'll go ahead and grab a resistor, and I'll make sure that this resistor is my 220 ohm resistor. That's the one with the two red bands on yours. It's going to look a little different, but ours do actually both have two red bands, so that's nice. And then I'm going to grab my LED, and I'll hook up the long positive leg to that resistor and the short negative leg to ground. If all goes well, if we've hooked this up correctly, the output of this last NAND gate that we've hooked up should be oscillating on and off at a consistent frequency. And that should be turning on and off this LED over and over again. Unfortunately, the simulator in Tinkercad is not great at handling this complex of circuitry, so it's not going to work, but I'll show you really quickly here on my breadboard on my desk that this does in fact work. So hopefully you can see this pretty well. It may be a little hard to see the connections, but it is in fact working. It does look a little bit different than I had it in Tinkercad just because of cleanliness on here versus what was going to look best on the screen. And you'll notice I didn't do a very good job color coding here, but we do have our power and our ground to the IC. And then we've got these inputs connected here, here, and here. We've got an output connected here and an output connected here. And then our two resistors and our capacitor to this common row on the breadboard, and our output out to here to our LED, which is in fact flashing. So I've used different NAND gates on here just to show you that it really doesn't matter which of the four you choose or even in what order, just whatever's going to make things cleaner and easier for you to understand. And one thing just to be careful of when you have resistors and capacitors that are stretching across long distances like this, just be careful that you're keeping them separate from each other so their leads aren't accidentally connecting and making a connection that you didn't intend on. So there you go. There's an oscillator made out of just NAND gates and a few other simple components. Very straightforward circuit diagram, but hopefully you're starting to get a feel for how this can kind of expand. We can take more and more logic gates and combine them in more and more interesting ways and eventually build out more and more complex systems. In fact, it's possible to build an entire computer system out of just NAND gates. It'll take, hundreds and thousands of NAND gates, but you can do it. And something really cool that you can look at if you're interested in this kind of thing is this course on the internet called NAND 2 Tetris. That's NAND, the number 2, and then tetris.org. And the first half of this course is actually free and goes through how you can actually start building a computer system out of just NAND gates. Very interesting. Everything's simulated, so it walks you through how to use this logic gate simulator software that lets you combine logic gates into systems and then combine those systems into bigger systems. And on the free coursework, you actually get all the way up to having a computer, and then it's just starting to write assembly code and then eventually the code of Tetris. And then you have the game of Tetris running on a simulated computer that's built out of only NAND gates. So that's pretty cool. But for this course, what else is there to do? Well, first I've put a little recommendation in here. Play around with some of these values and see what happens to the frequency of that flashing bulb. What if you replace this resistor? What if you replace this resistor? What if you change the capacitor for another capacitor? The only other one that you have is, I believe, a 0.1 microfarad capacitor. So that's going to be 100 times smaller than this. So what you might find is that maybe it is flashing, but it's flashing faster than your eyes can detect. But play around with that a little bit. One thing I want to note about this oscillator though, and you can see in this diagram here, is that the output is symmetrical. That means it's on for the same amount of time as it's off. So whatever that frequency is, it's basically split in half, on and off. There are some applications where we want to have a clock signal or a flashing light that is on for a different amount of time than it's off. Maybe we want it just on for a short bit and then a long pause, and then on for another short bit and then a long pause. Or maybe the opposite. We can't do that with this NAND oscillator, but we'll see later on we have another IC that I've given in your kit. It's called the 555, and you can make all sorts of kinds of oscillators with the 555. So we'll see that later on. The first thing we get into before we move away from the NAND gates is this concept of the half adder. This is a little bit of a taste of that NAND to Tetris course, a little bit of a look into how some of these basic computational elements inside of a computer could be constructed out of just NAND gates. And so I'll talk about that here, and I'll actually just leave it to you to try building for yourself a half adder and seeing if it works. And the next video that I do will cover some of the later stuff in the workbook. So let's talk briefly about the half adder and the CPU, and more specifically the ALU. So inside your computer's CPU, there's a bunch of things going on. The main thing that's doing the actual computations is what's called the ALU, or the arithmetic logic unit. This is a complex collection of logic gates that can perform a variety of different mathematical operations on binary numbers, such as binary addition, subtraction, multiplication, division, etc. Now, your CPUs in your home desktop computer or your laptop likely work with either 32-bit or 64-bit binary numbers. Now, all of this stuff about binary numbers and 64 bits and 32 bits, binary addition, what is all of this stuff? Well, right now I'm going to plop in a video for one of my other courses to explain the basics of how the binary number system works and what binary addition is all about. Well, the binary number system represents values, place values, as either zeros or ones. Our number system, the base 10 system that we use, any place value can take the value between 0 and 9. And if we're counting, we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And when we run out of digits, and we want to add one more, we return that place value back to 0, and we add 1 to the next place value. So now we have a 1 and a 0. And then add 1, so we get 1 and a 1, add another 1, 1 and a 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9. And now we've run out of digits, so we return that one back to 0. We add 1 onto the next one. So now we have 2, 0, and so on and so forth. Okay. Binary number system works exactly the same way, just instead of having 10 digits to work with or 10 numerals to work with, from 0 to 9, we only have 2 numerals to work with, a 0 and a 1. So what this means is, with a single digit, we can represent 2 numbers, 0 and 1. With 2 digits, we can represent 4 numbers. Okay, we can have 0, 0, 0, 1, 1, 0, 1, 1. We have 4 numbers we can represent with 2 digits. With 3 digits, we could represent 8 numbers. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. That was 8 numbers. So hopefully that makes a little bit of sense. Some of it might become more clear as I explain the next part, but at the end of the day, it's not really critical for this course that you understand how the binary number system works and how binary addition works, but you might be interested in this, so feel free to keep following along. This is basically how binary addition works if we're looking at just a single bit. If we're adding one digit of binary to another digit of binary. If we have a 0 and a 1 added together, we get a 1, just like in our base 10 number system. Same thing if we have a 1 and a 0 added together, that's a 1. If we have 0 plus 0, that's also 0. So all of this is the same. The only difference is when we have a 1 added to another 1, in our base 10 number system, that would be a 2, but in binary, we don't have the numeral 2. So instead, we set that bit down to 0 again, and we carry over to the next place value. With 1-bit binary addition, we don't have another place value, so nothing really happens, but we still will set that down to 0. So it might be a little confusing that I'm saying 1 plus 1 equals 0. Really what I'm saying is 1 plus 1 equals 0 with a carryover into the next place value. You can fill in the truth table for this system, just exactly this. We would get 0 and 1 is a 1, so that would be here. 1 and a 0 is a 1, so there'd be a 1 here. 0 and a 0 is a 0, and 1 and a 1 is a 0 with a carryover, but there's no room for that in this truth table. So you can see that other than that part about the carryover, we've basically got an XOR. This is exactly the same truth table for the XOR logic gate. Now, we could use the XOR. We'd have to do something else to handle that carryover, but it's a useful exercise to try building this logic system out of just NAND gates. And in doing so, we'll see how we could build an XOR out of NAND gates if we didn't have an XOR. So this is the circuit diagram for a half adder. And we call it a half adder because it doesn't take into account any carry from a previous adder. If we wanted to have 2-bit addition, 3-bit addition, 4-bit addition, etc., basically we just need a half adder, but that also takes into account carryover, and then we just chain those together, 1 for each bit. But for this quick example, since your NAND IC only has 4 NAND gates in it, we'll just do this half adder and we'll actually ignore the separate piece about the carryover. So essentially what we're trying to get is this XOR truth table out of these 4 NAND gates. And you can see the circuit diagram here, very simple, very straightforward. There's no additional hardware other than whatever you want to use for your inputs. So just like in the last video, you could use some slide switches for the inputs, and you could use an LED for outputs to visualize that. But you're just going to hook it up in this way. So you notice some of these inputs are actually connected together. The output goes to some of the inputs of some of the other ones, and then they kind of chain together like this. So you can try hooking this up on your breadboard and seeing if you get the XOR behavior on the LED out of your switches through this. Now, if you wanted to make a full adder, something that could account for that carryover, and then make a bunch of them and do 2, 3, 4-bit binary math, you would need 9 NAND gates per full adder. So in addition to these 5 for handling just the basic XOR logic and the carryover, you need an additional 4 NAND gates if you're going to start including a carryover that would be coming in. So a little bit beyond the scope of what you have to deal with. You could probably play around with this in Tinkercad circuits, though I don't know how well it will work given that it didn't work for our oscillator, but it could just be that it doesn't like oscillating things, but something like an adder might be doable. If you do that, definitely show me, but don't feel like you need to. And you can skip this as well if you don't want to go through this work. But the next video, we're going to cover the next section, which is more fun with ICs. So I've given you a handful of different ICs. The first one we'll look at, again, is the 555, and we'll see how we can make an oscillator circuit out of that using this circuit diagram. And then I've also given you a handful more and a brief description of what they do, and I'll leave it to you to come up with something interesting to do with them. You can hop on Google and search 555 projects, 4017 projects, and find some different things you can do, or you can just try and use your brain and look up the data sheets and see if you can figure out what they do on your own. We'll cover all of that stuff, the 555 and the other ICs, where to find their data sheets, what kind of things you can do in the next video. For now, we'll stick with our NAND gates, and you can try making the oscillator, and if you really want, you can make a half adder minus the carryover. So that's all for today. Take it easy and see you next time.